All right, let's jump right into it. Welcome to this explainer. Today we are tackling what is, without a doubt, one of the most critical global challenges of our time, predicting extreme weather. With climate change completely rewriting the rules of our planet's weather systems, the way we forecast water flow, specifically those dangerous, life-threatening floods, has got to evolve. And what we're going to explore today is absolutely fascinating. A recent scientific breakthrough has shown us how a new, highly adaptable mathematical approach could literally be the key to our survival. We're talking about moving away from rigid, old-school math and moving towards systems that can actually think and, adjust on their feet.
So, think about this for a second. Here is the high-stakes question to kick things off. How do you actually predict a flood before a single drop of rain even hits the ground? In an era where extreme weather is basically becoming the new normal, we rely heavily on predictive models. But what if those models are stuck in the past? Well, the answer, as researchers have recently discovered, lies in teaching our predictive models to actually adapt to the weather in real time. It's all about giving our math the flexibility to change its mind.
Okay, let's dive right into Section 1, the water prediction problem, and the rising stakes in a changing climate.
For decades, scientists have relied on traditional streamflow models to figure out how much water is going to end up in our rivers. But there's a huge catch in how many of these standard models operate. They essentially treat a light Tuesday afternoon drizzle the exact same way they treat a massive, catastrophic hurricane. I mean, it's wild when you think about it. The core issue here is that rigid math just outright fails in extreme weather. Standard hydrological models use what scientists call constant parameters. They just assume that the condition of the watershed, how the soil absorbs water, how it drains, never changes over time. But obviously it does. Because these models are stuck using those unchanging parameters, they consistently fail to capture the sudden, explosive reality of extreme storms. High-flow events are pretty rare compared to everyday weather, which means the models just don't get enough practice capturing that extreme variability. And that leads them to severely underestimate dangerous flood waters.
To really ground this problem in reality, take a look at these topographic maps. We're looking at 4 incredibly diverse catchments down in southern Thailand, which actually served as the testing ground for this new research. Now, this is a region heavily influenced by unpredictable tropical monsoons. The rainfall variability between the wet and dry seasons is just massive. In areas like this, a model that underestimates high flow isn't just some academic math error, it's a real-world hazard. Failing to predict a flood here has devastating consequences for communities, for agriculture, and for critical infrastructure.
So how exactly do scientists crunch the numbers on this? That brings us to Section 2. Meet the GR2M model, or as I like to call it, the sponge and the drain.
Okay, so GR2M stands for a rather long French name, Génie Rural à deux Paramètres Mensuels. It is a widely used, monthly, conceptual hydrological model, and it's incredibly popular because of its simple structure. It only needs a few types of data, like rainfall and potential evaporation, and it relies on 2 main interconnected conceptual reservoirs, which you can actually see mapped out right here. On the top left of the diagram, you've got the production store, and beneath that, the routing store. Rain falls into the system, some evaporates, some gets absorbed into the ground, and the rest eventually finds its way to the river, and the behavior of these 2 reservoirs is controlled by just 2 distinct mathematical parameters.
Let's look at the first one, parameter x1. You can literally just think of x1 as the sponge. Actually, in strictly scientific terms, this represents the maximum capacity of the soil to absorb and store water within that production store. When it rains, this sponge soaks up the moisture. But as we all know, when a sponge is completely saturated and reaches its maximum capacity, it can't hold a single drop more. The excess water just overflows and runs rapidly over the ground surface. Scientists call this quick flow or surface runoff.
And then right below that, we have parameter x2. If x1 is the sponge, x2 is the drain or, the plumbing system. This is the exchange coefficient that controls the routing store. Once water percolates deeper down into the ground, it becomes groundwater. x2 manages how this slow, gradual flow of groundwater moves around, how it's retained in the earth, and how it ultimately exchanges and routes itself into the river to become streamflow. So, to recap, you have x1, the sponge, handling the immediate surface absorption, and x2, the drain, managing all that deep, slow-moving water.
Which perfectly sets up Section 3, the parameter-switching solution, and teaching these models to adapt. All right, here is where the real breakthrough happens. The researchers realized a pretty fundamental truth. The sponge and the drain just cannot operate the exact same way during a bone-dry drought as they do during a torrential monsoon. The physical properties of the Earth actually behave entirely differently depending on how much water is hitting them. And this beautifully illustrates the contrast. On one side, we have the original model, GR2M. It uses rigid, fixed parameters. It forces the sponge and the drain to stay the exact same size all year round, totally ignoring the actual weather. But on the other side, we have the hero of our explainer, the newly developed GR2MS model. The S stands for switching. This model is flexible. It allows the parameters to adapt dynamically based on the incoming rainfall.
So they fixed it using this brilliantly simple three-step process. First up, they collected decades of historical weather and water data. Second, they used an AI data-driven technique called k-means clustering to sort through all that historical data and group the months into two distinct categories: low rainfall and high rainfall regimes. And finally, step 3, they programmed the model to automatically switch the X1 and X2 parameters based on whichever weather regime was currently happening. Now, the really crucial point here is that by splitting the historical data into these two totally distinct regimes, which you can see here as a low rainfall slice for normal conditions and a high rainfall slice for extreme storms, the model can now deploy a smart sponge and a smart drain. If the monthly rainfall is below a certain threshold, it uses the standard everyday parameters. But if a massive storm rolls in, the model instantly flips a switch and uses a completely different set of parameters that are specifically calibrated for extreme, high-stakes weather events.
Of course, a cool theory is great, but you have to prove it works. Let's move to Section 4, testing in Southern Thailand and actually proving this dynamic approach.
To see if this parameter-switching idea held up in reality, the scientists built out this incredibly rigorous testing framework. They took all their historical data from those 4 catchments and split it up. They used about 70% of the data to train or calibrate both the old rigid model and the new flexible model. Then, they took the remaining 30% of the data to validate it. Basically, they tested the models on past weather they had never seen before, just to see which one accurately predicted the real-world streamflow that actually occurred.
And wow, the results were honestly incredible. The flexible switching model, the GR2MS, just absolutely crushed the original. Across all these highly complex statistical metrics, the flexible model came out on top. The Kling-Gupta efficiency and overall index, which measure overall accuracy, both went up. The mean absolute error went down. But here is the most important part. The peak error for high flows decreased significantly. This means the new model was vastly superior at capturing those sudden, dangerous flood peaks that the old model used to completely miss. Overall, their combined performance metric improved by nearly 12%.
As part of the study, they also ran what's called a global sensitivity analysis, using this method called Sobel's variance-based decomposition, which gave us this really striking heat map. What they found was super surprising. While you might intuitively think the soil surface capacity, the sponge, would be the most important factor, it turned out that X2, the drain, actually had the strongest and most consistent influence on predicting streamflow throughout the entire year. Managing that slow, underground routing process is highly sensitive and absolutely vital to getting the math right.
All right, that brings us to our final section, a smarter, safer future. Let's look beyond just the math here. So we've talked a lot about equations, AI clustering, and all that, but what's the actual so what here? Why does this specific mathematical tweak matter to you and me? Well, it matters because better math directly translates to saving lives. By allowing hydrological models to switch parameters dynamically, we can build highly accurate early warning systems for floods. We can manage our vital infrastructure, allocating water sustainably for agriculture and dams, which, by the way, aligns perfectly with the UN Sustainable Development Goal 6. It's really about giving communities the tools they need to build climate change adaptation and resilience. Because when we know exactly how much water is coming, we can prepare, we can adapt, and we can survive. Ultimately, the big takeaway here is pretty profound. Extreme weather? It's kind of our new normal now. And our science, our tools, and our math absolutely must adapt just as fast as our changing planet. The GR2MS model proves that flexibility isn't just a nice feature to have, it is a necessity. So I'll leave you with this provocative thought to chew on. If we can teach our water prediction models to abandon their fixed rigid ways and dynamically adapt to reality, what other rigid systems in our world desperately need a dynamic upgrade? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll catch you next time.